Redox reactions involve a reactant being oxidized while another reactant is reduced. But in order to understand who's been oxidized and who's been reduced, you first must master calculating the oxidation numbers of compounds as well as elements. Without being able to do this, you won't know for sure who's been oxidized and who's been reduced. Now, when we talk about calculating the oxidation number, we break it down into two categories. We have our general rules and we have our specific rules. When it comes to general rules, we're talking about calculating the oxidation number of an entire element or a compound. Now, for an atom in its elemental form, the oxidation number will equal 0. When we say elemental form, that means that the element is either by itself, like we have with carbon solid, or it's connected to copies of itself, like Cl2, P4, and S8. This is also important. Not only does the element need to be either by itself or with copies of itself, but it must not have any charge present. They must be neutral. If that's true, then its oxidation number will be 0. Each of these have an oxidation number of 0. Now, for an ion, the oxidation number equals the charge. Here, oxygen is by itself, but it has a charge. So its oxidation number now is -2. Sodium here, its oxidation number is equal to its charge, so it would be +1. Here, phosphate, the entire molecule, or the entire polyatomic ion, has an oxidation number of -3. And then finally, ammonia, if we're looking at the entire compound, its oxidation number is equal to 0 because it has no charge present. When we talk about specific rules, that's when we're talking about finding the individual oxidation numbers of elements within a molecule or compound. Now, if we have a group 1A ion that's part of a compound, its oxidation number is +1. If we have a group 2A ion element within a compound, its individual oxidation number is +2. Then things start to get a little bit different from what we're accustomed to seeing with charges. Here, for hydrogen, it is +1 when it's connected to nonmetals. So here, hydrogen is connected to oxygen, so it's +1. It's still +1, and here it's +1. But once that oxygen connects to a metal or to boron, its oxidation now becomes -1. So in these cases, hydrogen's connected either to a metal or to a boron. Fluorine. Fluorine within a compound, it doesn't care what's around it. If fluorine is within a compound, its individual oxidation number will always be -1. With oxygen, it gets a little bit crazier. With oxygen, if it's a peroxide, it's going to be -1 for its oxidation number. A peroxide has the formula of X2O2, where X represents a group 1A element. So here we have hydrogen peroxide, sodium peroxide, and potassium peroxide. Notice the setup. It's 2 elements from group 1A connected to 2 oxygens. That's what makes a peroxide. Now, if it's a superoxide, its oxidation number will be -0.5. What's the general setup of a superoxide? Well, a superoxide is just 1 element from group 1A connected to 2 oxygens. Remember, X represents a group 1A element. So here we have potassium superoxide, cesium superoxide, and lithium superoxide. In these cases, oxygen would be -0.5. If oxygen is not in a peroxide or a superoxide, then its oxidation number will equal -2. Finally, halogens, which are elements in group 7A. They are -1, except when they're connected to oxygen. When they're connected to oxygen, we don't know what their new oxidation number will be. We will have to calculate it. Now, the exception to this, of course, is go back to fluorine. Fluorine doesn't even care if it's connected to oxygen. It's still always going to be -1 when it's within a compound. Now again, it's essential that you learn these rules for calculating the oxidation number of compounds as a whole, as well as individual elements within a compound. This is the first step to really understanding redox reactions. It's highly suggested that you memorize these rules, and then when we talk about redox reactions, remember the fundamental features of oxidation versus reduction.